Well, good evening, everyone. Welcome to Amateur Astronomers Incorporated, also known as AAI, for our weekly Fridays at Home presentations. AAI makes its home at William Miller Sperry Observatory on the campus of Union County College in Cranford, New Jersey. And since our observatory is closed at this time, we are holding our weekly presentations online. But on the third Friday of each month, from September to April, we hold our monthly meetings, which include guest speakers from various educational institutions around the country. Tonight's speaker is Dr. Emmanuel Shan. Dr. Shan is a Chamberlain Post-Doctoral Fellow at the Lawrence Berkeley National Laboratory in California. He received his PhD in astrophysics from Princeton University in 2017. Before that, he received his master's in theoretical physics at École Normale Supérieure de Paris, France. He's also an aspiring amateur astronomer. And the title of his presentation is A Cosmic Shadow Theater. So with that, Dr. Shan, would you please begin?
Great. Thank you so much, Mary, for the introduction, and thank you everyone for having me. I'm delighted to present some of my work to you all tonight. And tonight's presentation is going to be focused on the gas that surrounds galaxies. And so if you look at an image of a galaxy, you may not suspect it, but there's actually a lot of gas spread out very far away from this galaxy. And the reason you may not suspect it is that this gas would basically be invisible, except if you could catch this galaxy and put it in front of a bright light, the gas would show through its shadow. And so that's what this talk is about tonight, a cosmic shadow theater. You can think of it as a shadow theater where galaxies would be the protagonists. You can also think of it as a watermark on a bill or a banknote. And when you put that banknote in front of a light, what was invisible is now revealed. And indeed, through these shadows that I'll discuss tonight, a lot of the properties of this gas are revealed. So where is the gas, how much of it there is, but also how hot it is and whether or not it's moving. And for these reasons, these shadow images actually have a lot of important consequences in astrophysics. I should also mention that these results are very recent. They're presented in 2 papers that appeared online only a few weeks ago. So this is really fresh off the press, exciting new results that I'm excited to share with you. As Mary suggested, I thought I should say a few words about me and what I do before jumping into the topic. And so my day job is cosmology, which is the study of astrophysics on the larger scales. And 3 things that my work focuses on are the following: gravitational lensing of galaxies, or how the images of galaxies get distorted by foreground masses; gravitational lensing of the cosmic microwave background. I'll explain what it is, but it too gets distorted by foreground masses. And finally, the question of the large-scale distribution of galaxies in the universe, where they are, how they cluster. And none of this matters to this presentation, apart from the fact that these 3 things tell you about the composition and the history of the universe. But as Mary said, apart from technically being a professional astronomer, I am also an aspiring amateur astronomer. So I love DIY projects. I'm currently trying to finish my mirror grinding for an amateur telescope, and I like to put my photo camera on top of random DIY mounts and try to take photos of what I can with more or less success. And I think this is what's great about astronomy. It's the fact that both professionals and amateurs actually contribute to science. And here I just wanted to show one paper that I really like. This is a paper from Donald Brandt's 2018. And basically what he did there, it doesn't really matter, but the point is he used advanced off-the-shelf equipment. And with that, he made the most precise measurement to date on this particular topic. So I think this illustrates how all amateur astronomers also contribute to science in this field. And so I wanted to thank all the amateur astronomers in the room for their contributions. And I thought I might also show this, because I think not everyone may know this, but actually all astrophysics research articles are available online for free to everyone. And so these are the 2 key websites: Cornell's archive.org and NASA's astrophysics data system. Anyone can go on there, and you'll find all the state-of-the-art research articles that are published every day. And if you happen to produce yourself state-of-the-art results, this is where it would be a good place to post. And in fact, tonight's results were publicly funded, and naturally the results are publicly available. You can find them on these two websites, and here are links to the two papers. So this is it for this part. Let's now talk about holding galaxies in front of a light and looking at their shadows. And before doing this, I wanted to give a bit of motivation for this. Why do we care? And start with explaining it with an analogy. So if for a minute you stop being an astronomer, you stop looking up at the night sky, and instead you look down on Earth at the night sky, this is what you might see. You might see bright specks of light, and these are city lights all around the world. And so if you're, for example, an alien and you'd like to know where the people are, perhaps for the purpose of world domination or any other reasonable purpose, your first guess might simply be that there are more people where there is more light. And that would indeed be a pretty good guess. So here's a map of the population density on the globe, and the two maps look fairly similar. So that's a pretty good guess. But they're not exactly identical. There are places here or there where you may not see too much light, but the population density is high. And also everywhere, the light, as you can see, is very concentrated in very bright, isolated specks, whereas the population is much more diffuse. And what we say in this context in astronomy is that the light is not a perfect tracer of the mass of people, for example. It's more concentrated. It's a biased tracer of the mass. And in fact, the same thing happens when you actually look up in the universe. So here's a simulation, and the bright dots you might see here are galaxies. So this is not an actual photo of the sky. This is a simulation of galaxy formation in which galaxies form, and you can see those bright dots, those galaxies there. And if you ask, in this image, where is most of the mass? The answer is the following. And this image may shock you. It looks very different from what you're used to seeing, images of dots or galaxies or stars. And that's because actually most of the mass is not in these stars or galaxies. It's in this diffuse gas. So here are the two images I just showed you. And more quantitatively, we know that only 5 to 10% of the total ordinary matter, so that is the matter that makes up you and me and my computer and stars, so only 5 to 10% of this matter resides in stars and galaxies and emits light. So the majority of the matter in the universe, 90 to 95% of it, actually resides in this diffuse gas that's much more spread out, and that is basically, for practical purposes, invisible. So this has been called the missing baryon problem in astrophysics. Really, this means missing ordinary matter problem. And it's a problem for a number of reasons. Well, first of all, as an astrophysicist, you'd like to think that you're studying the universe, not just 5% of it. And so you'd like to know where most of the mass is. So you'd like to find where this gas is. And second, this gas and its properties, where it is, how hot it is, holds a number of clues about galaxy formation and other interesting things that we care about in cosmology. And so if you were able to detect this gas and measure its property, you would learn a lot of interesting astrophysics. And so this was our motivation. Now, the question is, okay, all the matter, most of the matter is in this gas and you can't see it. How can you detect it? And so the question is, how does one detect gas? And so the way I do it usually is I just wake up and try to breathe, and if it works, it tells me that there's gas. But you can't really do that with those galaxies. You need to find something else. And in fact, there are many other ways to detect gas, and you are doing it every day. If you look up at the sky, what you might see is the sky looks blue. And what you're seeing the gas in the air. And the reason you're seeing it is because there's a bright backlight behind it, the sun. And so as light travels through the gas, as the light backlights the gas, the light interacts with the gas, and this is how you detect the gas. So the blue sky, the orange sunset, this is all an effect of having a backlight behind that gas. And this is exactly how we would like to detect that gas. So that seems fairly simple. You just need to send a very bright light into space, wait for a few million years, it will get behind a galaxy. When that happens, turn on that flashlight and just try to see if you see the shadow of the gas. So the idea seems simple. In practice, it doesn't seem very feasible, except for one thing. And you might think of this as us being very lucky, but it turns out the universe already has a built-in backlight, which is behind all of the stars and all of the galaxies that we can see. And this is the backlight we're going to try to use. This backlight is called the cosmic microwave background, or CMB. And what this confusing diagram is trying to explain is basically the history of the universe. So here would be the Big Bang, and us today would be on this side. Between us and the Big Bang, about 14 billion years of evolution. And this cosmic microwave background is basically the first light we see from after the Big Bang. So this is a relic light from the Big Bang. And this light travels through all the universe to reach us. And every now and then, it's going to bump into galaxies and their gas. And so what we have here is a natural backlight that we can use to measure the gas. Okay, so that's somewhat lucky. What does this backlight look like exactly? So here's an all-sky map of this cosmic microwave background, this backlight. And it basically looks like noise. There's some blobs, some are red, some are blue. To give you an idea, the blobs are typically a degree aside. And this is our backlight. For the purpose of this talk, we don't really care about those fluctuations. In fact, if the CMB could be perfectly uniform, that would make our life easier, but the fluctuations are there. And I should mention that actually studying those fluctuations in the microwave background is what taught us about half of what we know about the history of the universe, meaning its age, its composition, and its evolution. So don't get me wrong, those fluctuations are extremely important, but for the practice of this study of using a backlight, they're not important. And this cosmic microwave background is just a backlight. Okay, so right, as I said, the blobs are about a degree on the side. And we'd like to look at this map and see if we can see the shadows from the gas around galaxies. And so we need to zoom in on this map, and we need to produce images with very high resolution because our galaxies are not a degree on the size. They might be more like an arc minute or an arc second. And to do this, we used a telescope, which I'll tell you about. So right, you want to detect those shadows from the galaxies on the cosmic microwave background. So here's the telescope that I'll tell you about. Here are the galaxies with the gas around them. And here's your background, your backlight, the cosmic microwave background. And so what will those shadows mean? So we're used to thinking about shadows with, a light like the sun and an object like your hand, and you see a dark projected image of it, and that's the shadow. What does a shadow look like in this case? So this cosmic microwave background, it turns out, is microwave light. And so the shadow from the gas is not simply what you would expect from the shadow of your hand in the sun. And in fact, it has a name. That shadow is called the Sunyaev-Zel'dovich effect, named after Rashid Sunyaev and Sunyaev-Zel'dovich, who first predicted the effect in the 1970s. So these shadow effects have been predicted a long time ago, and we would like to measure them. I should say, you may have seen on this slide, there are two sorts of such effects, the kinematic and the thermal Sunyaev-Zel'dovich or SZ effects. And the nice thing about this is that if you can measure those shadows, you can actually distinguish between those two effects. And those two effects, those two shadows, tell you different things about the gas. The kinematic Sunyaev-Zel'dovich effect tells you about the motion of the gas. So for example, if that galaxy and the gas around it is moving towards you or away from you, this will be imprinted on this shadow. And so if you can measure it, not only have you localized the gas, where it is and how much it was, you know whether or not it's moving. So that's the kinematic SZ effect. The other shadow, this thermal SZ effect, actually tells you about the thermal motion inside the gas, and so how hot it is. So if you can measure this shadow, you know how much thermal energy is in the gas. So that's kind of nice. It's a bit more than a normal shadow of your hand. It tells you not only the shape of what produces the shadow, not only where the gas is, but it also tells you whether the gas is moving and how hot it is. Okay, so these are the shadows that we're after. And as I said, we'd like to zoom in on this map on a very small patch, the size of a galaxy, and see if we can detect and resolve those shadows. And to do this, we use data from this telescope. This telescope is called the Atacama Cosmology Telescope. And so it is located in Chile, in the Atacama Desert. And the reason you would want to put your telescope there is that there's a mountain there, Cerro Toco Mountain, and the height, the altitude of this mountain is 5,000 meters or 17,000 feet. So it's extremely high, one of the highest observatories on the globe. And one consequence of this, also being in the desert, is that the air is extremely dry. And this too is a very desirable feature for a telescope looking at microwaves, because the humidity in the air does emit microwaves and mess up your image. And so short of going into space, you want to be as high as possible and as dry as possible. And this is where this Atacama Cosmology Telescope was built, getting first light in 2007, so a few years ago. And the telescope sits inside this ground cover, hidden by this ground cover, which protects it from radiation from the ground. This telescope, the ACT Atacama Cosmology Telescope, is not the only one on this mountain. We have some friends there, the Simons Array and class, and soon a new experiment joining us, and I'll say a few words about this. So if you look inside this ground cover at the telescope, so here's the ground cover and the telescope is inside. This is our telescope. It's an off-axis Gregorian design, so that tells you about how the mirrors are shaped and oriented towards each other. And the primary mirror is 6 meters. So that's a fairly large telescope. And the reason for this is, as you guys know, in astronomy, the resolution of your map depends on the size of your primary mirror. And with such a mirror, 6 meters, the kind of resolution you achieve in the microwaves, to look at this backlight, is about arc-minute. And to give you an idea, arc-minute is about the resolution of your eye. And it's also about the size we expect for the gas around those galaxies. The technology that goes into this telescope is actually really cool. Because you're observing microwave light and not optical, the detectors are very different. And in fact, the whole detector has to be cooled to below a degree above the absolute zero. And the detectors are the so-called superconducting transition edge bolometers. So these are pieces of silicon that are cooled exactly at the point where they would transition to superconductivity. And this is where they are extremely sensitive to any incident microwave light. So I've described the telescope, the experiment, where it is. Most important is the people who work on it and collect the data and reduce it and make it usable. So here's an image of a lot of the ACT collaborators at our latest meeting in Princeton, New Jersey, so not very far from here. You might be able to find me somewhere in the back. And what I wanted to point out is the fact that people who work on this experiment come from very many different institutions in many different countries. And so to collect this kind of data and do this kind of measurement takes a lot of people. That's it for the description of the experiment and the team. Let's look at the images that come out. And so the image I'm showing here on the left is a zoom in of the map of the cosmic microwave background I showed earlier. And so those blobs that are red and blue, you now see here, but you also see a lot of noise, a lot of specks. And that's a problem. And as I said, these images of those blobs, the red and blue, which for this project we don't really want, those blobs are degree size. And the images of the galaxies and the gas around them is more like arc-minute. And so on this map, they would be expected to look like dots. And in fact, this is why this ACT experiment is so useful. It improves the sensitivity and the resolution of this map so much that you can start to see those dots. And those dots are the size that you want, the size that you would expect. And so you might think, perhaps we're done. These are the shadows of our gas. it turns out we're not quite there yet. So these are indeed signals from individual galaxies, but they're not shadows. They're actually microwave emission from these galaxies. And they're not exactly what we want. In fact, if you look at this image, you do not see the images, the shadows that we're looking for. So that's somewhat disappointing. And so when that happens, you can ask yourself, why is that? Why am I not seeing the signal that I'm looking for? And a good way to answer this question is to ask, well, how large was your signal to start with? And this question is something you can answer with simulations. So here are simulations. On the left, a simulation of that backlight, the cosmic microwave background, with again those random degree-sized blobs. On the right, a simulation of the galaxy shadows that I'm looking for. Those shadows are about arc-minute on a side. And if you know how to read color scales, you'll see that the fluctuations in this backlight, the variations in the brightness, this number 300 microkelvin, as opposed to about 2 microkelvin for my signal. So the signal we're looking for, those shadows from the gas around galaxies, are about 100 times fainter than the intrinsic fluctuations in this backlight. So that's a problem. Basically, what it says is you're trying to look at the shadows of the galaxies using a backlight, but that backlight is not uniform at all. And the variations of brightness of that backlight, 300 microkelvin, are much larger than the shadows from your galaxies. And so how are you going to detect it? So the first approach, which is probably very reasonable, is to just say, this is too bad, that was a good try. We built this experiment, collected all this data, but the signal is just too small. So that's the end, and I should probably stop my talk there. But I think a lot of the amateur astronomers in the room know that this is not what you do when your signal is small and your noise is large in your astronomical image. What you typically do in that case, so you have an image, it's crappy because the signal is small and the noise is large. What you do is you stack. And what that means is you measure the signal, you take many, many images and you average them together. So you can't really take many, many images from the same galaxy because your noise here is not changing, it's just the background. But what you can do is take the image you see for every galaxy and average them together. And then the fluctuations in this noise will cancel out. So sorry, this may have been a bit confusing. So if there's any question about that, feel free to interrupt me. But this process is called stacking or averaging images. And I think it's familiar to all the astrophotographers in the room. And so this is exactly what we decided to do. Let's just stack the signal, average the images around each galaxy. Now the question becomes, okay, how many galaxies do you need to measure and average together to detect your signal? And for this, there's a very good rule of thumb, and it pretty much works with everything. And the rule of thumb says that if you have one good image of something is equivalent to many, many, many bad images of the same thing. And how many do you need is the square of the ratio of the signals. So, okay, my signal is 100 times smaller than my confounding background. And so how many galaxies do I need to stack? 100 squared. Okay, 100 squared is 10,000. And so if I want to detect those shadows, I need to average the images from 10,000 galaxies. Now, 10,000 galaxies might seem like a lot of galaxies, and indeed it is. And so the question becomes, where can I find the positions of so many galaxies in order to average them together? And in my field, when that happens, when you need a lot of galaxies, you always do the same thing. What you do is ask the boss. The boss is the Baryon Oscillation Spectroscopic Survey. What those words mean doesn't really matter, except that it's a survey of galaxy. And so it covered a large part of the sky. And every time a galaxy was found, its 3D position, so position on the sky and how far away from us it is, was measured and recorded. And I have visualized these galaxies here. So this plot may be confusing, but you should think of yourself as being at the center right there, just because that's where the telescope was. And the telescope happened to look out in some directions, so in this direction and in that direction. And every time a galaxy was found and its 3D position measured, I put a dot on this figure to show the galaxy. In the background of this image, I've added the backlight of that cosmic microwave background. And to show you that these images are measured in 3D, you can rotate and you can look at all these galaxies from whatever angle you want. So you have those 3D positions of galaxies. And in fact, you have 400,000 galaxies, which is more than the number we need to be able to detect the signal. And what this means is that in principle, if we do things right, if we stack or average the images of the backlight at the position of each of these galaxies together, we should be able to detect our signal, which is the average shadow from the gas around those galaxies. Now you may be wondering, how does one measure the positions of so many galaxies? And the answer is the Sloan telescope at the Apache Point Observatory. This is the telescope that you see there. And the way all the positions of those galaxies were recorded is actually right behind me. So I happen to have a bit of that telescope at home. And what you see here, this disk was placed on the focal plane of the telescope. And you may notice it has a lot of holes through it. And the holes were drilled where the galaxies were found. And in each of these holes, a fiber optic was placed to measure the spectrum of the galaxy and therefore its distance. And the survey would go through a bunch of these plates every night and observe different parts of the sky and measure all these galaxies. All right, so we now have all these galaxy positions in 3D. We have those high quality maps of this backlight, this cosmic microwave background. All those galaxies are in front of the backlight. Can we average all those images and measure that shadow, that signal that we're looking for? Let's do it. So here's an image of a small cutout around a galaxy. To give you an idea, if you were to zoom in on the central pixel in this image, this is what a typical galaxy in our sample would look like. And this is an image from the Hubble Space Telescope, a small telescope that no one knows about. Just kidding. This is the Hubble Space Telescope, and this is what an image of those galaxies look like. That galaxy would fit inside the central pixel. And what we're going to do is add more and more of those galaxies in this image, stack more and more images, and see if we can detect any shadow. Before we do this, you might notice that I have some white circles on this image. The inner white circle is the resolution of our ACT telescope, so about arc-minute resolution, like your eyes, remember. And the outer circle here is the extent of the gas that we expect to see from theory. And so one question might be, does the gas actually have that size? I'm going to go through this video, which progressively adds more and more objects to the stack. This video lasts 4 seconds, but you should really think of it as 1.5 years of my work and years of the work of all these people in the collaboration photo that I showed you. So this is really an accelerated version of it. And so, okay, every second that elapses in this video, every second that elapses, a few thousand galaxies are added. So this will go really fast. And what you can see is that at step 0, when you have only about 1,000 galaxies, you do not see anything in this map. This is just noise. You do not see a shadow in there. And so as you add more and more galaxies, you start to see that shadow pop out at the center of the image. And this is our measurement. So this is the average shadow from the gas around those galaxies. You can see that the blob, the dark blob, this shadow from the gas, is relatively similar in size to what you would expect. You can also see that this size is much, much larger than the size of the galaxy itself. Remember that galaxy fit in the very central pixel of this image. And so you can see the gas is way more extended than the galaxy you see. And this is one of our key results. We're able to measure and detect this gas, which would be invisible otherwise. Now, something else you may have noticed on this image, there's not just a dark blob, there's also a light blob at the center. And so why is the shadow brighter at the center? This makes no sense. In fact, what this is that the gas doesn't just block the light and act as a shadow. The galaxy itself at the center emits microwave lights. And this microwave light at the center basically fills in the shadow and makes it bright again. Okay, so this is our stacking measurement. Maybe I'll run through it a few more times. So remember, about a year and a half every 4 seconds. So at the start, you don't see anything. And as you add more and more and more and more galaxies, you start to see that shadow appear. Okay, so let me summarize those measurements. We used data from the Atacama Cosmology Telescope, as well as Planck, which I showed earlier. And using this data, we were able to measure the shadows around those galaxies, where, remember, the typical galaxy would fit in the very central picture of each of these images. Now, you can see here I'm showing 3 sorts of shadows, and they all look different. You may remember earlier I talked about those different sorts of shadows that the gas can do when put in front of that microwave light. One was this kinematic SZ, which, remember, tells you about how much gas there is and whether or not it is moving. And your eyes may be able to see a bright dot or bright blob at the center of this image. And this may be the most crappy looking astrophysics image you have seen in a while, but it actually is the highest signal to noise measurement of this effect to date. So you are now looking at the most precise images of the motion of the gas from those galaxy shadows. So this is actually a pretty cool image. So this was this kinematic SZ, one of the sorts of shadows. The other sorts of shadows, remember, was the thermal SZ, which tells you about where the gas is and how hot it is. Turns out where it is times how hot it is the pressure of the gas. And so this is what you see. And then the image that I just showed you earlier with the bright blob at the center, this dust emission. The reason you do not see here is because we have methods to null the dust emission. And this method was applied in this image. So now you see the full shadow. So these were the key results of this measurement. And so the highest precision measurement of this type of shadow and the motion of galaxies to date, and highly precise measurements of this other type of shadow, which tells you about the gas pressure. And these measurements have a number of important consequences. And they are a bit technical, and so I won't go into too much detail on this, but I'll just say a few things. One, you now know where the gas is, how it is distributed around those galaxies. And this is a key input to our understanding of galaxy formation. And the reason is as follows. When galaxies form, stars form inside those galaxies, and those stars can explode in the form of supernova. When that happens, this explosion pushes the gas far out of the galaxy. And so just how far out is the gas extended around the galaxy tells you about how powerful the supernova are. And the amplitude of this effect of, say, supernova is actually one of the largest uncertainty currently in our understanding of galaxy formation. So by measuring these gas profiles, you have a key input to our galaxy formation model, and you can learn a lot about this. Another thing you can learn, and I mentioned it really quickly at the start of this talk, is dark energy. And I won't say much about this, except for the fact that it is one of the biggest open questions in physics today. And our ability to measure its properties, it turns out, depends on our ability to know where the mass is in the universe and how it's distributed. And this is something you cannot do if you don't know where most of the ordinary matter in the universe is. And so if you haven't localized the gas, you cannot learn about dark energy as much as you'd like to. And so these measurements will actually help us learn about dark energy much more. And so these are some of the important consequences that these measurements have. This is only the beginning of those sorts of measurements. So we expect much better images to appear in the next future. And this is why. So we talked about the BOSS, this survey, so part of it being here, which collected information about so many galaxies. Here is one of the successors of the BOSS. It's called DESI, the Dark Energy Spectroscopic Instrument. And this is an instrument that's on the Mayall telescope in Kitt Peak, Arizona. And I was fortunate enough to be allowed to help with the commissioning of this instrument. And these are some images I took of the telescope at the center of this image while the commissioning was happening. And so first light has happened. This survey is collecting data. It got delayed by a few months because of the coronavirus, but observations are about to resume in a few weeks. And while the BOSS experiment was able to look at many galaxies at the same time, this experiment will look at many, many more galaxies at the same time. It's a 5,000 fiber spectrograph. What this means is that in any single image, in any single exposure that this telescope takes, you are looking at 5,000 galaxies simultaneously. And what this means is that about a year from now, we'll have so many more galaxies that the precision in our images of the shadows is going to increase by a factor of 3. So wait a year and those images will get a factor of 3 times sharper. So that's the improvement on the galaxy side. It turns out there's also going to be improvement on measuring the backlight itself, this cosmic microwave background. And this is the new large neighbor that's going to arrive next to our Atacama Cosmology Telescope. It's called the Simons Observatory. This is an experiment that is funded and the construction is underway. To give you an idea of what it looks like inside, you have again a mirror whose size is about 6 meters, a second mirror, and the cryogenic detectors. Now, if you ask how large will the focal plane, the detector array be on this telescope, the size of this opening here is about the size of a full-size king bed. So that's an extremely large focal plane packed with cryogenic detectors. And the result is we'll be able to make much more sensitive, much more precise maps of the microwave skies, and in particular of those shadows. So if I can just summarize what I presented to you, the things that might be worth remembering. First is that the gas around the galaxies, that gas which is typically invisible, actually contains most of the ordinary matter in the universe. And so if you see optical images of galaxies and stars, you are missing a lot of the mass. And this is what we call the missing baryon problem. Now, this gas can be detected if you have a backlight behind it through its shadows. And it turns out the universe is kind enough to have a built-in backlight, this cosmic microwave background, which is the first light from the Big Bang. This cosmic microwave background is very important in itself, and I didn't say anything about that. But for the purposes of this measurement, it provides a backlight from which you can measure the gas shadows. And so those shadows reveal the gas. They tell you where it is, how hot it is, whether it's moving. And so they let you observe those 95% of the ordinary matter that you wouldn't be able to see in any other way. And if you're interested in more technical details about this, feel free to look at the papers, which are publicly available online. And so thank you everyone for your attention. I'll stop there and take any question there might be.
Okay, Dr. Sean, we have a few questions. We have 2 questions, both from Jim Nordhausen. The first question is, which SZ effect is used to find galaxy superclusters?
Right, that's a very good question. And so I mentioned that there were 2 sorts of SZ effects, the thermal and the kinematic effect. And those 2 scale differently with the mass of the object you're looking at. And so here we were looking at small objects, galaxies or galaxy groups, but indeed there are much more massive objects in the universe called galaxy clusters. So these can have 100 to 1,000 galaxies in them. In fact, they're the most massive bound objects in the universe, galaxy clusters. And the SZ effects offer a way to detect and study those clusters. And in that case, it is the thermal SZ effect. And in fact, for those massive clusters, I did not show it, but if you look carefully at this map, you see bright spot in red. So these are just, these are not those SD effects, but you also see some faint blue spots. And those faint blue spots actually are those thermal SZ shadows from galaxy clusters, much more massive than simple galaxies.
Okay, and with regards to the telescopes in that you were displaying earlier, Jim Nordhausen comments, looks like South Pole telescope, but smaller.
Both good points. Indeed, it looks like the South Pole telescope because those two experiments are observing at very similar wavelength or frequency. They're both observing the cosmic microwave background, so microwave lights. And so it makes sense that they would look similar. For example, one way in which they look similar is that the mirrors are actually segmented. They're pieces of metal put together. And one reason that's possible is when you observe at microwave frequencies as opposed to optical light, the wavelength of the light is no longer a fraction of a micron, which is fraction of a hair. The wavelength of the light is actually millimeter, which is pretty big. And when you observe a millimeter wavelength light, your telescope doesn't need to be much smoother than a fraction of a millimeter. And that's really easily achieved with plates of metal put together. And so basically, this is why building a telescope in microwave, in a sense, is cheaper because your surface accuracy of your mirror doesn't need to be as good. But the counterpart to that is because you're observing at long wavelength, to get a given resolution, you need a very big mirror. And that's why ACT and the South Pole telescope are a very big mirror. And in fact, they both make very complementary measurements of the cosmic microwave background and very complementary measurements of these SZ shadows that I presented today.
Okay, Cliff Ashcraft asks, you have gained a large improvement by S over N by averaging large numbers of galaxies, but have lost the information about the individual galaxies. I would imagine that larger galaxies would be surrounded by larger clouds. Any way to deal with this problem?
Yeah, that's a very good question. So indeed, that's exactly what happens. So you gain signal to noise, you reduce your noise by averaging the signal from many galaxies. But by doing this, you no longer measure the shadow from one single galaxy, you measure the average shadow. And so if your sample of galaxy has some very big galaxies and some very small galaxies, you measure the average of that. In practice, one way you can get around this effect is by having a sample of galaxies that is very uniform. So if you have a sample of galaxies that are very similar in sizes or in any other properties. And this is sort of what we did with this bus sample. This is a sample of luminous red galaxies. And so it's basically as uniform as it gets in terms of sample of galaxies. Now, as you saw, we barely had enough galaxies to make one good image of those shadows. But in the next few years with DAISY and the Simons Observatory, which I presented, we'll have so many more galaxies, the signal to noise will be so much higher that we will be able to split the sample based on any properties that we care about. So for example, if you have galaxies that are redder or bluer, you can split the sample in two and measure the shadows of one or the other. If you have galaxies that are at higher redshifts, so farther back in time or closer to us, you can split your sample this way and see how the shadows evolve in time. And so basically, once the signal to noise becomes good enough, you can start to answer very interesting questions about evolution of the shadows and the properties that they describe.
We have another question from Jeff Glazer. I may have missed the discussion, but what is the composition of the gas?
Right, that's a very good question. And in fact, the one property which is both a strength and a weakness of those shadows is that it is insensitive to it's mostly insensitive to the composition of the gas. And so you cannot use those shadows to learn about the composition of the gas. There are other ways to do it. But the reason we actually like this, and it's a good feature for us, is if you want to know about the mass of gas, without having to assume anything about the composition, those shadows are the only way to do it. But to answer the question of what is the composition is mostly that of the average universe. And so about 76% hydrogen by mass, about 24% helium by mass, and traces of the rest. But that's a very good question, because in fact, it's one of the selling points of those shadows, is they let you know how much mass of gas there is without assuming anything about the particular composition.
All right. I've made an invitation to the attendees that the next question will be live, but no one has a question. So with that, I'll turn it back to you, Mary.
Sorry, everyone. Okay. Thank you, Manu. So join us every Friday night at 8 p.m. online. Our next presentation next Friday is the implications of the cosmic silence, or so where is everybody? That's going to be by AAI member Dr. Al Gottlieb. And again, Manu, thank you very much for your presentation. It was very interesting.
Well, thank you very much for having me, and thank you for all the really good questions. It was a pleasure to be here.
Okay, and thank you for joining us, everyone, and we're wishing everyone clear skies.